Well, hi guys. Well, here we go. Fasten your seat belts because this is the last leg of our journey together. We're looking at the normal distribution, which is our example case study distribution of a continuous random variable distribution. Okay, off we go. There it is. Now, it's a very interesting looking beast. It is a PDF and it is the most commonly one used, I'd say, out there in society. It's got uses everywhere, including the results of your exams. Would you believe it? Yeah, that's true. So there's the function there. I've written it up on the top left, and you can also see it here around. That's the actual function that I've drawn. So yeah, okay, so here's some properties of it. Put it in a nice big red box for you. It's a PDF, yes, it's a probability density function because the area under the curve is 1. It's symmetric, and it's single-peaked, yes, you can see that, and it's bell-shaped. It's called the bell curve, commonly called the bell curve, okay? Now, the mean, mu equals 0. You can see that, I've just shown you that there, mu equals 0. And also, the standard deviation is 1, okay? The standard deviation is 1. So I've represented that there for you. I found 1 on the x-axis there, and I've put that there for you so that you can see on either side of the axis. It's symmetrical about the y-axis. Standard deviation is 1. Okay, there you go. Now, what else can we tell you? Yes, it's called the standard normal distribution. Okay, that's the name given to it, the standard normal distribution. The version of it which has got a mean of 0, standard deviation of 1. Because really, guys, this whole thing, when we study normal distributions, unfortunately I have to tell you, it's all about transformations. Yes, it is, because very few normal distributions would have actually those characteristics of a mean of 0 and standard deviation of 1. They're usually off-centre and quite different standard deviations. So we've got to know how to interpret the transformations that they've undergone. Okay? Yes, we do. Right, now, what have we got here? Oh, I'm just wanting to show you there on the calculator. I've done an area under the curve calculation from minus infinity to plus infinity, the integral of the function, and I got 1. So that's verified that it's a PDF. Next one, I'm doing the expected value. There's x times f of x dx integral of from minus infinity to plus infinity, and I get 0. So that verifies that the mean, that's the mean, is 0. Okay, you can do that for yourself too. It's a good exercise. And we're going to also look at the expected value of x squared, because as we found in the last chapter, we need that information for working out our variance and our standard deviation. So that's it. Integral of x squared times f of x dx from minus infinity to plus infinity gets us 1. So the expected value of x squared is 1, okay? Which will lead to a standard deviation of 1, because the variance would be e of x squared minus e of x all squared, which would be 1 minus 0, which is 1. Therefore, the standard deviation being the square root of 1 would be 1. Okay? Now, here we go, guys. Fasten your seat belts. Fasten your seat belts. Dilations and translations, okay? Right. Now, for non-standard normal distributions, this is what we're going to study. What about if the standard deviation wasn't 1, okay? Which is pretty well normally the case, guys, pardon the pun, normally. Okay, what about if sigma, which is the symbol we use for the standard deviation, what if it was 2? Now, here comes a graph. There you go. Now, that shows you, the blue graph there is the standard normal curve. This one, that's the standard normal curve, and then the red graph is the one where you're using a standard deviation of 2. So you can see it's dilated out that way, like out that way in the x direction. Okay? So let's just emphasize, I'll show you how you get that effect. There's a random point on the blue curve, which is the standard normal curve, x and y. Now, if you were to dilate that by a factor of 2, which you can see that there, that function there? Yeah, see, we've dilated it by a factor of 2. That number there, the denominator, the term under the vinculum there is 2, and that is the dilation, the x dilation, e.g. from the y-axis, but the x dilation, and that therefore forces that point to morph into that position there, which becomes 2x and y. Okay, get that? Very good. And there's the other one, corresponding one on the other side of the y-axis. And we're saying that's an x dilation, in the x direction that is, of a factor of 2, which you can see that now, can't you? Like it's fattened right up, going out in the x direction, but nothing's happened to the y side of it, okay? From the y-axis, that's what I'm saying. That's the proper way you're supposed to refer to it. But I always say in my head it's an x dilation before I say anything, because that to me is the logical way to think of it. Okay. All right. So yes, that's f2 of x, which is f1 of x over 2, where f1 of x was the blue curve. f1 of x is this one down here, see, which is the blue curve. There it goes. Right. Okay. Now. So therefore, I'm writing out the function in full for you, where I've substituted there x over 2 for x, and that's the function that you get. Okay, can you see that? Are you happy with that? Okay, now we've got an NB, okay? NB, guys, NB. There is a problem, yes? And the problem is that we've dilated that blue graph, which had an area under it of 1, We've applied a linear scale factor of 2 to it along the horizontal direction. So it ain't got an area of 1 under the graph anymore. It's now 2, because we've multiplied the x dimension, everything in the x dimension, by 2. So we've got to do something about this, because if we want it to be a PDF, because it sure isn't anymore, okay, it's not a PDF. So what can we do? We want to preserve the new x positions, because they're representative of this expanded standard deviation of the function, okay, of the red function. So what do? We have to preserve the x values as they are, but we can apply a fudge factor to the y values. In fact, we can shrink all the y values of that red curve by dividing them by the same factor that we applied to the x, the dilation factor we applied in the x direction, which was 2. So we can divide them all, the y values, by 2. That's what we're going to do. Scale the y down by 2, okay? Now, I think I've got this over the page for you now, so stand by. Oh, yeah, right, okay, just a minute, what am I doing here? Yeah, now, here comes the graph, right? Here comes the graph, ready? There it is. Now, it looks crazy, but look, don't worry, look, this is the blue original standard normal, okay? This is the one which we basically dilated by a factor of 2 out in the x direction, okay, but it's not a PDF anymore because it's got too much area. So we've divided all those red y values by 2, and we've shrunk the height of it down to half. And we've got the black curve, which is f3 of x, which is a half of f of 1 of x over 2, whereas this one was f1 of x over 2. So it's a half of it. So this, guys, this black function is our probability density function, which applies for that situation where we had a standard deviation of 2 instead of 1. Okay? And its areas are all preserved. Everything works fine. So what do? We've got x and y from the original blue standard normal graph. That goes to get the dilation of a factor of 2, standard deviation of 2 in the x direction, we get 2x and y, and then what do? We halve all of the y values to get the black one, which is 2x and y over 2, and that black graph is a PDF again, okay, it's valid. Okay, do you get that? Yeah, that's what you do, okay, so you have to compensate by shrinking, adjusting, scaling the y values according to whatever dilations you apply in the x direction. Yeah, that's the function which I was just explaining. Yeah, okay, and I'll put a half in front to halve all the y values. Okay, so the area under f3 of x is 1, and yes, it is a PDF. Okay, all right. Now, how's that? How's that sitting? All right, good show. Right now, so well, what happens now if we had not only this situation happening, we had sigma equals 2, but what about if we start changing Mu now, the mean, okay? What about if mu wasn't naught, like it is in the standard normal curve, okay? E.g., what if we make mu equal to 1? Okay, well that's the mean. Now the mean is where the hump is, the hump on the bell curve, okay? So if we make the mean 1, I think you can see that that's going to shift over the hump to where x is 1, isn't it? In fact, it's a translation. Whoa, translation in the x direction of 1 unit. Now, this is the original graph there. That's the dilated one for the expanded standard deviation of 2. This is the black one, which is half the height of the red one, which gets us back into PDF land again. Okay, but still with a standard deviation of 2. And this pinky one here is translated. It's the black one, but translated over by 1 unit to the right. Okay, and if you have a look at this very cunningly contrived formula here, you'll see it reflects that in the formula. Look, it's a half, which is the half of the height bit, and it's got the 2 down here, which is the standard deviation of 2, the dilation of a factor of 2 in the x direction or from the y-axis, and then the x minus 1 basically means it's shifted the whole graph over 1 unit. So you can see this is Transformation City, isn't it, guys? Yes, I told you, didn't I? All right, so there's the new hump. That's when x is 1. Okay. Yep, and that is an x translation of 1 unit to the right, as I was explaining, okay? Yeah, and that's the formula, which I was also just explaining. So f4 of x equals, now I've just written it out in full for you, there it is. The f4 of x is, now 1 over 2, that's your compensating thing for the dilate, that's to basically make the height half as much, that's the sigma term. This is the same as it was before. This bit's the same as it was before, but that there, you've got your x minus 1, which is your translation to the right by 1, over 2, which is your x dilation of a factor of 2 for the standard deviation of 2, all squared. Okay, you get it? Good. Alright, so what does all this stuff mean? Well, you may well ask. Let's summarise. So, we've got a normal distribution we're talking about here, which is the case study distribution, continuous random variable distribution case study. Okay, and we've got something called the standard normal, f of x equals that thing, okay, which we've been describing, mu equals 0 and sigma equals 1, okay, so far so good. Now let's go for the non-standard normal. Okay, now this is where the formula is. Now I've put the bits in red that are different from the above, okay? So you've got to have this little thing down here to compensate for your height adjustment. Yes, okay. To compensate for this dilation here in the x direction, and that is your horizontal translation in the x direction, moving the mean from the central axis, symmetrical about the y, okay? Are you happy with that? Okay, so mu is the mean translated from 0, yes? Yes. In our case it was to the right, that's what that arrow means. And sigma is the standard deviation, which is the x dilation factor of sigma from the y-axis, alright? I think that's okay. So far so good? Good. Good, good, good. Now, both of these guys have they both have an area under the curves of 1 because the areas are preserved by our bit of fiddling with the height of the y when we have a horizontal dilation bit in the x direction. And they're both PDFs. Yes, they are both PDFs. Yes, they are. Right, that's the end of that. Now, we're going to have a look at some theory now, so don't worry. We're going to nail this stuff now. In terms of straight transformations, what do we need to say? Well, I'm going to compare the standard with the non-standard, and we're going to come up with what I call the key to everything, which just makes everything clear. So don't worry about a thing. The fog will lift, guys. Now, there's our standard form, standard thingy, you know, standard normal. Now, there's my transformed one. You notice that I've used a dash with the y to make it very clear that that's a transformed variable. This one's got a dash on it as well to make it very clear that that's a transformed variable, okay? Now, what we're going to do is we're going to get them both in what I call equivalent form. Now, equivalent form means they've got to look the same, okay, with no stray terms floating around. So that thing there is the odd man out. He doesn't belong. So he's got to be got out of there, okay? And if he isn't inextricably bound up with the x stuff, which he isn't, then he becomes a y term, okay? And I'm going to put him over there with the y. These guys here, the root 2 pi, they're in both of those expressions, so that's their equivalent, that's all right. Okay, so I need to just take care of this little beast here, then I'll have equivalent expressions. So I've written it out like that. Now, I know that looks very strange with this. It's, you know, why didn't I just write it as sigma y dash? Well, there is a reason, because when you have a transformed function, what's on the denominator, guys, is the dilation factor. So the dilation factor applied to this transformed function in the y direction is 1 over sigma. And I can see that easily as long as I express it as a denominator. That's why I do it. You might not want to do it that way. That's fine, that's your business. You do whatever you're comfortable with. But that's the way I like to do it, because I can see that that's the y, that's a y dilation, and I can see that similarly and correspondingly, and this is an x dilation. So it's very easy to see. That's what I'm saying, it's very easy to see. Alright, now let's go for the key to everything, guys. We're going to compare the y's with the y's and the x's with the x's, and everything will become as clear as crystal. Okay, so therefore, what am I saying? I'm saying that this, in that expression on the right, is equal to that in the standard normal expression on the left. They are equivalent. They are equivalent. What else am I saying? Now, let's do the x's now. Yeah, I'm saying that this x thing here, in here, is exactly equivalent to this x thing here. Okay, they are. They're absolutely equivalent. Now, let's just, that is what I call, guys, I'll put a big, big blue box, thank you Mr. Box, around it. That is what I call the key to everything. It's da-da-da-da, get the trumpets, the fanfare, get the orchestra, you know, and get the... get whoever you can get to come and celebrate with us, because we've got to the key to everything. So, yes, it's the key, and I'm going to put a key there. It's the key for you and me. Now, from that key, you can easily then tell what your recipe is for making one in terms of the other, or transformed in terms of standard, or standard in terms of transformed. I'll show you what I mean. Let's go first of all for the transformed ones, okay? Now, we can see that, therefore, y dashed is y over sigma, isn't it? Yes, it is. Yeah. Y dash is y over sigma. And we see that x dash, if I've just rearranged that expression there, that expression there a little bit, I get x dashed is equal to this thing, sigma x plus mu. Now, that tells you the recipe of how to get y dashed and x dashed very easily. In other words, to get y dash from the standard normal, you simply divide it by sigma. Now that's what we did, wasn't it? You remember that? That's what we had to do to fiddle with it, to make it a PDF again, okay? Because the x dash, the transformed version of x, do you remember what we did? We dilated by sigma, which in our case was, what was it again? 2. Standard deviation of 2. We spread the whole thing out by 2, then we moved it over by 1, which was our version of mu. See? Look, so you just read it off. You just read it off. It's that easy. That's why it's the key to everything, guys. So, do you see that? That's what you do when you're getting x dash and y dash from x and y. Now, if we do it the other way around, and we make x and y the subject, which they kind of are in the blue box, but we'll just refine it a little bit, you get y is equal to sigma y dashed, and you also get that x is equal to... right, you get, where am I? You get y equals sigma y dash. Now, what am I saying there? So, I'm saying to get y from the transformed version of y, which remember was scaled down, you're going to multiply it by sigma to scale it back up again. That's what you do. And in order to get the standard normal x value, you do exactly what we did in reverse to get the transformed value. You take the transformed value. The last thing we did was move it over by mu, or we're going to shove it back to the left by mu. Now it's centralised around the y-axis. Now we're going to shrink it down by dividing by sigma, which is exactly what we did in reverse order to actually get the transformed version of x in the first place. So look how easy it is to see what to do, guys. It's so easy. So please do this. Get them in equivalent form, this one, that one, then compare the y's with the y's and the x with the x's, and everything. You have the key to everything. Everything becomes clear. Okay? It's just so good. Yes, I need boxes around them because that is a momentous little step. Yes, and that's what you do when you're getting x and y from x dashed and y dashed. Very good, guys. How do you feel about that? Right, so we're going to go over the page and we're going to start from exactly the same point as we just got to. Right, now, what do we got here? We've got the standard normal distribution, haven't we? Yes, we have. Now, so if we plot, now I want you to really concentrate here, what I'm saying here. If we plot sigma y dash, now just see, I've just put a circle around there, okay? I put a circle around there. If we plot sigma y dash on the y, right? I've already just got y on the y and x on the x for that blue curve you can see in front of you. But if I plotted also, overlaid on that, sigma y dashed, yes, which I'm saying to you is the same as y, aren't I? Yes, okay. And I plotted on the x, if I plotted on the x-axis, this thing here, x dash minus mu all over sigma, which is up here. Now what's that equivalent to? It's equivalent to this, isn't it? Okay, so if I plotted that thing on the x-axis, okay, let's just show it. There's the y. There's the y there, the sigma y dash I'm plotting there. And I'm also going to plot down here what I just said, and that's going to be x dashed minus mu all over sigma. Now, my question to you is, what do you think? What do you think the curve would look like? Okay? What do you think the curve would look like? I think you've worked it out, okay? It would exactly overlay the blue curve. Exactly. You see, because it is the same curve, because those transformation steps are the steps you need to do to the transformed values of y dash and x dash to get them back to y and x. Oh, ain't it exciting? Okay, so therefore, from henceforth, guys, we are going to rename the standard normal variable, not x anymore, z, or z if you're in the United States, okay? But we call it z. So, okay, so our standard normal variable is just being changed in honour of its significance and in order to avoid confusion from x to z. Okay, there's a z. So yes, so the amazing thing is that those two graphs, guys, the blue standard normal graph and the transformed back version, in other words, the that overlaid one where I've plotted. Wait a minute, what have I plotted? I've plotted this thing there versus that thing down there. It gets me exactly the same graph because they are the standard normal variables again. That's the deal. Yeah. Now it's very useful, as you'll work out, but I need to go over the page to show you why it's very useful. There's my blue standard normal graph there, and there is my pink non-standard normal graph, which has basically it's been height adjusted down by half to adjust for the fact that it's been dilated in the x direction for a standard deviation of 2, and it's been shifted over to the right by 1. Yeah? Now, okay, just recapping, the blue one has a mean of 0 and a standard deviation of 1. This pink one's got a mean of 1 and a standard deviation of 2. Now, okay, for f4 of x, which is the pink one, let's take a value. Let's just take a value of x just to see, just to compare the two graphs, and I'll show you some of this very interesting stuff. Yeah, that's f4 of x, yeah? That's the pink one. Now, where x is 4, I've just picked where x is 4, okay? And what I'm going to do is I'm going to shade in all the area under that graph where for the parts where x is greater than 4. Yeah, there it is, and that area is equivalent to the probability the probability of x being more than 4, or even greater than or equal to 4, okay? So that is the probability, okay? That is the probability that x will be greater than 4. Now, let's work out what the standard normal value would be equivalent to x being 4 on the pink, for the pink one, okay? Now that's what z is, okay? That's what z is, and that's what you would get if you morph that 4 back to its equivalent position on the standard curve. That's how you would do it. That's the recipe for it, okay? Because they are equivalent. So we'll take 4 minus, 4 minus 1 over 2, and we get to 3 over 2. Now let's mark that in on the blue curve. There it is. There it is. Now, if I was to mark in the area that's under the blue graph, for which z is greater than or equal to 1.5, right, there we are. Now, here's the thing I want to explain to you. Those areas, ladies and gentlemen, those areas, because the areas are preserved, okay, for equivalent corresponding parts of both graphs, which they are equivalent, when x is 4 on the pink graph is equivalent to when z is 1.5 on the blue graph, because the areas have been preserved, ladies and gentlemen, those areas corresponding to probabilities for the pink one that x is greater than 4 and for the blue one that z is greater than 1.5 will be equal. They will be equal. That's right, this area, this probability here, this probability there, because the areas have been preserved, is equal to that area there because those probabilities, the areas have been preserved and the probabilities are the same. The probabilities have to be the same because they're equivalent points in both those curves. How do you like that? It's pretty amazing, eh? So we're going to generalise now. We're going to generalise. We're going to say that, okay, the probability that x is greater than something, okay, A we'll call it, will be the probability that z is greater than its equivalent position on the blue curve, which would be A minus mu over sigma. Okay, that's what we're saying. And you can say the same thing about less than. I've just done an equivalent less than statement down there underneath. Okay, are we making progress? I think we are. I think we are. All right. Yep, good. Now, just to hammer the point home finally here, I'm just going to look at the two graphs again. I'm going to show you something, okay? Now we've got an area. Okay, this is the area between 1 and 2 standard deviations for the blue standard normal curve, and that'll be at 1 and at 2 because the standard deviation of that curve is 1. Now we'll look at the same thing, equivalent thing, for the pink curve. Now you remember that had a mean of 1, standard deviation of 2. So 1 standard deviation would be 1 plus 2, 2 standard deviations would be 1 plus 4, which gets us to 3 and 5, are the equivalent parts of that pink graph for 1 and 2 standard deviations of it. Yeah? Right. Now, the areas, that is the probabilities, are the same. They are the same. Those areas are the same because the area preservation has been adhered to by scaling down that pink curve so that it's not as high, it's half as high as the blue curve. Yeah, there you go. Now, all right, now, just to finally get the big badoomch here going. To get from x to z, right, to get from x to z, pink curve to blue curve, let's just show you what to do again so you'll really get it. I'm going to pick a point on the pink curve at standard deviation 1. Okay, look at where x equals 3 on the curve. There it is, I just crossed it. Do you see that? I just put a cross there, right? So now, hopefully if I apply that x minus mu over sigma thing, what I'm hoping I will do is I will get from there back to the x position at here, there, because that's the standard deviation, 1 standard deviation for the blue curve. Okay, that's what I'll do. And then to get to the actual position point on the curve, all I've got to do is multiply it up by 2, because this pink curve is halved in height, and I should get bingo right up to there. Okay, so let's do it. We'll do the practical example of it. So we've got x take mu. That means, what does it mean? Yeah, it means what I've done there is I've taken 3, taken away 1, right? And I get to 2. That's mu gone, okay? Now that should, ladies and gentlemen, put us back with a centralised pink curve symmetrical about the y-axis, which is not obvious from what I've done there, but still that's what you should get. It's now centralised back again around the y-axis. Now, what am I going to do now? I'm going to divide by sigma, so therefore I'm dividing that 2 value by sigma, which is 2, so that should get me back to 1. There it is, look, it's there. It's there. I'm back on the standard deviation of the blue curve. I'm back on the standard deviation of the blue curve. So you can see that it does work. Okay, it does work. So it's the same as the Z value. It is. So therefore you're convinced, yeah, blue box is necessary because that's a pretty big, amazing practical demonstration we've just done, right? And just to get, if you multiply that Y value that you see there by 2, to counteract and undo the height adjustment thing we did to preserve the area under the curve equaling 1, you'll get back to that point there, which is exactly the point on the blue curve which gave rise through our sequences of transformations in the first place to get to there. Okay, do you get that? It's pretty good. Yes, yes. There's a smiley face for you to say how happy you are. Well, I am anyway. Yeah, the Y times sigma gets the same point on the standard curve. All right, does that hammer the point home? Hope so. We'll do a couple of examples and we'll get out of here, okay? Now, what do we got? Probability density function, normal, random variable x is that thing there. Hello, Mr. Funny looking function. Now we have to write down the mean of the standard deviation, then we have to sketch the graph. Well, no problem, guys, no problem. That's A. Now we're going to do A. We've got to write down the mean of the standard deviation. Well, you can see, come on, what's the mean? The mean is here, this point here, yeah? I'm thinking backwards, getting tired. So, right, do you see that? That's where the mean's been shifted to. That's the standard deviation. That's the height compensating thing to compensate for the fact that we've actually dilated it out by a factor of 10, which is pretty enormous, okay? All right, so let's do that. We've got there's your function, and what am I saying? Hence, yes, sigma equals 10, which is the standard deviation, and mu is 3, which is the mean. I've got it right this time. Okay, now here's the graph. It's pretty underwhelming. It's actually pretty awful because this thing is such a flat looking thing. It actually peaks at 1, 2, 3, but you wouldn't know it, would you? It looks like just a flat line. It does peak, but I wanted to show you this curve in relation to the standard normal curve, which shows you the amazing transformation in shape. Okay, but I have done another version of it, scaled right up without the blue curve, so you can see it is actually what we said it is. All right, that scale there is minuscule. See, that's 0.062 up to the top there. See, so and we've got little graduations of 0.005. So this is, you know, that's a very, very small microscopic rise, but you can still see it's a normal distribution curve. Yeah, get that? Good. Can we go on? Good. Now we've got transformation throughout the nation, guys. Describe the sequence of transformations which takes the graph of the probability density function of the standard normal distribution to the graph of the probability density function of the normal distribution with those things. Okay, this one here, mu's 3 and sigma's 2. This one here, mu 3 and sigma's a half. This one here is mu minus 3 and sigma's 2. Here's your standard function for reference, and here's the transformed one. Okay, that's the general version of it. Now I'm going to put the numbers in. Okay, there they go. There they are. Right? Yeah, there they are. Now, what we've got to do, ladies and gentlemen, is we've got to compare the y's with the y's, and the x's with the x's, and all that stuff, and get the key to everything. Or if you feel confident, you can just read it off with the Dr. T technique, okay? D, then R, then T, dilation, reflection, change. There's no reflections, it's dilation, and if there were any reflections, and then translations is the order in which you have to quote them. Okay, so you could see if you were doing that where would we be? We'd say, all right, this thing here, the y has been shrunk down to a half its normal size, so that's a dilation of a factor of a half from the x-axis, isn't it? Yeah. This is a dilation of a factor of 2 in the x direction, or from the y-axis. This is a translation of 3 units to the right. So you can just read it off if you can do Dr. T, or else you do the key to everything. Here it comes. Here's the key to everything. So we compare the equivalents in the equivalent forms. Okay, you've got to get that 2 out of there because it doesn't appear here. You've got to get that 2 out of there. It doesn't belong to the x's, so you get it over here with the y's, and that statement is then very valid. Okay, this one, and then that equation, and then you get there's your x equivalence. Okay, there's your x equivalence. See, you've got this stuff in here, and you've got that original just x sitting up there by himself in that equation there. So now you can get your key to everything. Okay, and we want the transformations, so we're going to make x dash and y dash the subject. There they go, and there they go. Now you can just read it off now. Read it off. So what is it? Yeah, there's that one. So that is basically a y dilation of a factor of oh yeah, it's a half. That's right. I'm reading it off directly. I'm not reading in reverse like the Dr. T technique. I'm reading directly. Okay, so that means you take the y value and you halve it. Right? That's what you're saying there, okay? Don't get confused. This is not the Dr. T thing is the reverse technique, okay? Everything's in reverse. You think in reverse, but this is the direct approach. This stuff. Okay, so that one's there. And what else are we saying? You look at that one there, and you can see, well, I can tell you that's an x dilation of a factor of 2 from the y-axis, then 3 units to the right, isn't it? Yes, it is, yeah. And yeah, so it gets you to the same result. It gets you to the same result, but that's a safer technique. If you're not so good at Dr. T, that's a much safer technique. I can feel a box coming. Thank you, Mr. Box. All right, now next to B. Now it's your turn now. You're having a try. Turn the video, pause the video, and I'll just hang around for you. And then when you're ready, unpause it, and then I'll show you what I got, and you can see whether you agree. Okay, you're back. Good. Okay, there's my transformed function for B, okay? There's the transformed function for B. Okay, so I'm going to do the key to everything technique, guys. Okay, so I'm doing the equivalence statements here, all right? That's the equivalent y statement. That's the equivalence x statement, and we just make x dash and y dash the subject, and then Bob's our uncle again. Yeah, good, that's that. That's that. And no, just read it off now. Let's just read it off. Okay, that means that the y has been multiplied by 2 this time, so that's a dilation factor of 2 from the x-axis. This is the x has been halved, so that's an x dilation of a factor of a half, which is from the y-axis, and I've moved it 3 units to the right. Let's see if that's what I said. Hope to goodness that's what I did say. Yes, I think that's what I said. That's an x dilation factor of a half, that's right, from the y-axis. Yeah, good. Good, and translation of 3 units to the right. Good. Mr. Box. Thanks. Over the page for C. Now you're going to do C. Off you go. Pause the video and then come back. I'll be waiting. Right, you're back? Good. Now, there's my transformed function for that situation they've given us. You agree? Good. Now, there's my standard normal one for reference. Now I'm going to do the key to everything again. The equivalent statements, there they are. There they are. Yes? Agree? Good. Okay. Now let's just make x dash and y dash the subject. Good. X dash the subject. Good. And read it off. Yeah, from that one we can say that y is down to a half. So that's a dilation of a factor of half from the x-axis. And the other one is that one, so we can say that x has been dilated by 2 from the y-axis and it's been moved 3 to the left. 3 to the left. Good, is that right? Yeah. Oh, ace, we got it right. We got it right, guys. Well, that's it. That's my little show. It was a long one, so I tried to keep it moving so you didn't sort of fall asleep and go insane on me with all those transformation stuff, which I know is pretty awful. There's the box, and there's the yes, you can do it. You can do it, guys. So, plenty of practice for you, and then we'll see you next time, okay?